A mechanism, then, is just the sequence of events that describes the actual process on how those reactants go to products. Like, how do you go from the top of the snow lifts down to the base lodge? Sometimes reactions are going to happen in one step, and sometimes they'll take several steps. Each of the steps, whether there's one or several of them, is referred to as an elementary step. And I'd like to show you a video now of an elementary step reaction. This is a one-step reaction where fluoride is displacing chloride. You end up with a fluoromethane, even though we started with a chloromethane.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
Notice that transition state. There were actually 5 bonds around carbon, 3 hydrogens, and there were dotted lines to both fluorine and chlorine. That's definitely a transition state where the activation energy is highest, because carbon doesn't like to have 4 bonds, and it certainly doesn't stay there very long either. This reaction is exothermic because the product's energy is lower than the reactant's energy. If the product's energy would have been higher than the reactants, it would have been endothermic. Finally, because there were 2 reactants, the fluoride and the chloromethane, we would call this a bimolecular reaction. Bi, in this case, means 2, so 2 pieces come together to make products. Bimolecular is what you'd refer to it as. The molecularity of the process just says how many pieces, molecules, atoms, whatever, are involved in the elementary step. Now remember, most reactions we're going to look at will be single steps, but you can have more than one step too. So if you had just one piece breaking down to many pieces, or more than one piece, it would be referred to as unimolecular. Down there you can see the very first one in that list. Unimolecular means A is breaking down to products, but there's only one reactant. Okay, bimolecular means you're going to have at least 2 pieces coming together to make products, and they can be the same, like A plus A. They could also be 2 different things, A plus B, all right, and those are all possible. Once in a while, you'll have termolecular, which means 3 pieces coming together, and they can all be the same. They can 2 of them be the same and 1 different, or they can all be different, whatever. Notice the rate laws. Because these are elementary reactions, single steps, rate law literally equals K times whatever the reactants are. This only applies, again, if it's a single step. Some reactions do occur in a single elementary step, but most reactions do take a sequence of individual steps to make the overall version. So again, that fluoride reacting with chloromethane, that was a single elementary step, and those are pretty cool. But most reactions, like this ozone breaking down to oxygen reaction, it's a series of elementary steps. So ozone breaking down to oxygen has been studied extensively, and what they feel is that it's a 2-step mechanism. The first step, which is unimolecular, is ozone breaking down to oxygen and an oxygen atom. And oxygen atoms are pretty reactive because oxygen likes to be a diatomic. Have no fear of, ice clear brew, oxygen was the of, okay? So that oxygen atom reacts with a second ozone molecule to make 2 oxygen molecules, 2 O2s. So the overall reaction is 2 ozones making 3 O2s. And notice there that the oxygen atom appeared and disappeared. We'll talk about that in a little bit.
Gaseous ozone decomposes in 2 steps. First, 1 oxygen atom splits off. Next, the single oxygen atom reacts with a second ozone molecule to produce 2 molecules of O2. The product of the overall reaction is 3 O2 molecules.
When you're writing an energy diagram for a multi-step mechanism like this one right here, every step has a hump in the diagram. And so you can see in the picture on the right there, this has two humps. And the first hump would be for step 1. The second hump there would be for step number 2. And so the energy of activation is usually, for us anyway, going to be the first hump's energy, so the arrow that's up and down right there. But it could be the second one too, and those special examples of that. So again, every step has a hump in the diagram, and the number of humps will tell you how many steps are in the mechanism. This is exothermic. Once again, reactants are at a higher energy than products, or products are lower energy than reactants. Exothermic.
Hydrazine is formed in aqueous solution in a 3-step process, each step being bimolecular. First, a molecule of ammonia reacts with a hypochlorite ion to form chloramine and a hydroxide ion. Next, the chloramine reacts with a second molecule of ammonia to form a charged species with a nitrogen-nitrogen bond. Finally, the charged species reacts with a hydroxide ion to form hydrazine and water.
There are lots of reasons why you shouldn't add bleach to household cleaners with ammonia. Lots of them, and you can look them up online. But one of the reasons is that the two of them together can make hydrazine, N2H4, which is actually a type of rocket fuel. Now, most household cleaners have ammonia, NH3, and the active ingredient in bleach is a hypochlorite ion, which is OCl-. So what you're seeing here is the reaction of two ammonias and hypochlorite to make hydrazine, water, and chloride, the part there at the bottom in yellow. Now, if I was just to show you the diagram on the right, you can see that there are 3 humps, all right? 1, 2, 3. And those 3 humps, and again, maybe I should highlight them. 1, 2, 3. Those 3 humps mean there's a 3-step mechanism. And so what they propose is that the first step is ammonia reacting with hypochlorite. It makes a compound called chloramine, NH2Cl, which is super nasty, plus some hydroxide. The second step, that chloramine, is pretty reactive, so it reacts with another ammonia to make a protonated hydrazine, that N2H5 plus thing, plus chloride. And that protonated hydrazine will react, in this case with hydroxide, to make regular hydrazine and water. So the overall reaction here, 2 ammonias and hypochlorite make hydrazine plus water plus chloride. So again, pretty interesting. 3-step mechanism, 3 humps. This is also exothermic, going from reactants to products. Again, no adding bleach to any household cleaners. It's not good. This is only one of the bad reactions, believe it or not, that can happen. So be careful. Don't do this at home, kids. The rate determining step, the RDS, is the most important step when there's more than one step in a mechanism. And the rate determining step is literally the slow step. And it's the slow step which determines how fast the reaction goes, which is interesting. But even more importantly, because it's rate determining, the rate law, all right, remember how we use the rate law to find out first order, second order, zero order reactant, stuff like that? The rate law will tell you what reactants are in the rate determining step. So here's an example of that iodine clock reaction. It's 2 iodides plus hydrogen peroxide plus 2H plus acid, making the blue purple iodine, I2, plus 2 waters. The rate law for that reaction is rate equals K times iodide times H2O2. Notice that both iodide and H2O2 are first order reactants. So for the mechanism, that means the slow step is going to have 1 iodide and 1 H2O2 coming together. The slow parts are in the rate determining step, all right? And the rate law will tell you what the reactants are. So in this reaction, because the rate law, first order iodide, first order H2O2, that means in the rate determining step that there's going to be 1 iodide iodide and one H2O2 coming together to make something else. So you can make just about any mechanism you want. Multiple steps, single step, you can have cosmic rays, whatever, but you have to have the rate law reactants correspond to your rate determining step in your mechanism. Otherwise, your mechanism isn't worth anything. This is also why the rate law orders of reaction are not necessarily the same as the stoichiometries. So if you look at this reaction, the iodine clock reaction again, it's 2 iodides plus hydrogen peroxide, but in the rate law, iodide was not second order, it's first order. So the rate law says that at the slow step, 1 iodide reacts with 1 H2O2. You have 2 iodides, but the second iodide is involved in a later fast step. Only the slow rate determining step has 1 iodide and 1 H2O2. So don't necessarily think that the stoichiometries of your reactants will equal the rate orders. It all depends on the rate determining step and the rate law. So here's the iodine reaction once again, and a scientist has proposed the following mechanism for this reaction. And notice here how we have step 1, step 2, step 3, but also we have slow step, and fast step, all right? And that's good. The rate law, which had to come from experiment, showed iodine was first order, H2O2 was first order. And sure enough, in the slow step, step 1, there's 1 H2O2 and 1 iodide. So in this reaction, in this mechanism, the 1 H2O2 and the 1 iodide makes hypoiodous acid, HOI, which is a weak acid and a weird one, plus hydroxide. And then the hypoiodous acid reacts with the second iodide to make iodine, I2, plus hydroxide. And then finally, the third step, hydroxide plus H plus making water. This is classic acid base and no problem. Well, if this is a good mechanism, then all of the steps together should give you the overall reaction, this one up here. So let's do this real fast, all right? Hydroxide and hydroxide on the product side cancel the 2 hydroxides on the reactant side. HOI cancels this HOI. We have H2O2, which is good, just 1 H2O2. We have 2 iodides, which are right there. We have 2 H pluses, which are right there. That makes iodine and 2 waters, which are both right there. Hey, that part of this mechanism is good. All of those individual steps combined together give you the overall reaction. But the other thing you have to have, this is a good mechanism, is that the slow step must correspond to the rate law reactants. So the slow step here should have 1 iodide and 1 H2O2, and it does, all right? That's what's in the slow step. This is a pretty good reaction, all right? The H plus is not involved in the slow step at all. H plus is considered a zero order reactant. So let's stop right there. Zero order reactants are still important for the chemistry. Like making the iodine clock reaction happen, you must have H plus, but they're part of the fast steps. So the H plus is zero order. Rate law means what is slowing our reactions down. And in this problem, the rate law is the iodide and the H2O2. The H plus is needed, but it's involved in the fast steps, not as important. So the bimolecular slow step is reflected in the rate law. And if all the steps together give you the overall reaction, which we did, we figured out, and if the rate law reactants equal the reactants in the slow step, which they do, this is a legitimate mechanism. So again, if you don't have both of those things followed, where you add all the steps and they give you the overall reaction, and the rate law reactants and the slow step reactants are the same, then you won't have a legitimate mechanism. But this one is legitimate. We checked them both. We are good to go. The reaction of NO2 and CO is thought to occur in two steps. There's a slow step and a fast step. So knowing that that's the proposed mechanism, and if the mechanism is legit, which of the following rate laws would correspond to this mechanism? So again, the punchline here is that the slow step reactants will be the ingredients, if you will, of the rate law. And if you look at that slow step, two NO2s are coming together and there's no CO. So if there's two NOs, you could write this as rate equals K times NO2 times NO2, or if you combine the two NO2s together, rate equals K times NO2 squared. NO2 would be a second order reactant here. And notice here that CO didn't appear until the fast step. So CO would be considered a zero order reactant. Step one, again, is considered the RDS, the rate determining step. The slow step is what determines how fast a reaction goes. A reaction is no faster than the slowest step. So in the hydrogen peroxide reaction, turning into the iodine, which is the clock reaction, step one, bimolecular. And again, the rate law says the iodide is first order, H2O is first order. That says that the slow step should have one iodide and one H2O2. And you can see in this slow step, that's exactly what we've got. So this is a good mechanism. Another comment should be made about HOI and OH minus. HOI and OH minus appear and then disappear, and those are called reaction intermediates. They're species that are around for a little bit, but they're used up right away. And if you have a mechanism and someone doesn't like it for some reason, you will bolster your argument for your mechanism if you can detect HOI and or OH minus. And they might be around for just a little bit, but if you have someone that's really good with lasers in chemistry, they can often detect these intermediate species for just like milliseconds or even nanoseconds at a time. So intermediates can be really important. An intermediate will appear in a mechanism and then disappear before the reaction's done. So in the overall stoichiometry, you don't see any HOI or OH minus for that matter. So mechanisms can be really cool. A catalyst sometimes will appear in a mechanism as well. Catalysts are usually used up at the beginning and regenerated at the end. Then also don't appear in the overall stoichiometry of the reaction, but they will be used up right away and then recreated at the end. Intermediates are created usually right away and then used up towards the end, so it's a little bit different. So this is a possible mechanism. There's two possible choices here. And what's happening here is they're substituting of an iodide by a chloride ion. So if you see here, one of the final products is CH3Cl, and you start with CH3I. So you can imagine that mechanism 1 and mechanism 2 are coming from two different chemistry labs, and they're kind of having an intellectual discussion about which one it is. So you can see that in mechanism 1, the slow step is the methyl iodide, CH3I, breaking down into some weird stuff, and then that reacts with chloride to make CH3Cl. In mechanism number 2, the methyl iodide is reacting with chloride directly to make a CH3ICl, a 5-coordinate carbon species. That's going to be slow because that's not easy to do, but that will then subsequently break down further into methyl chloride and iodide. So what they find in people when they actually measured then the experiment part is they found that the methyl iodide is a first order reactant. So rate equals K times CH3I to the first power. And notice that there's no chloride. So if chloride isn't part of the rate law, that means that the chloride is a zero order reactant. And if you have a zero order reactants are not part of the slow step. So what the rate law here is telling us is that in the slow step, you will have one CH3I only. That's the only thing you're going to have. And if you look at those mechanisms, mechanism 2 would have methyl iodide and a chloride. So if the rate law would have been first order with chloride instead of zero order, mechanism 2 would have made more sense. But in this problem, no way. Mechanism 1 is the way to go. Methyl iodide is first order, and chloride is then by default zero order, which means it's not part of the chemistry. Mechanism 1 in the slow step has just a methyl iodide. Mechanism 1 is the one that I would put my money behind. That makes the most sense based on this data.